Thank you everybody to for joining this session and following me today. Yeah, as I said to Anas, it's really exciting. I'm really excited to be here. It's a vibrant community. I'm gonna give you a little bit of background about me. So I'm Olivier Chappe. I'm a senior solution architect for AWS, Amazon Web Services. I've been there for 3 years now. And today I'm working in the same team as David that did a presentation previously. I mean, I'm working for the game tech branch of Amazon Web Services. As a background, I've been working in for Ubisoft before during 13 years, so I'm a little bit familiar with the video game industry. I've been working in places like France, China, and Canada, and I see that there are other vibrant community that are really interesting. Um, I also co-founded a startup after my experience at Ubisoft, and it was native on AWS. And at the time I started in 2010, we didn't have as many services as there are now. But my goal today is like to try and introduce you to those latest services and explain you how I think they can be helpful to modernize game development. So here is the agenda. First, we'll talk a little bit about game production and game live ops and how serverless can enter the stage and simplify it. And I'll show you a little bit of example. I had the opportunity to help one of my customer develop. This example is also available on GitHub in the AWS sample. So there will be a link at the end of the presentation for you to go and have a look if you want. So game production, where when you're developing a game, the art of your business.
Olivier, can you adjust your microphone a little bit because
You can't
your
hear me?
voice a little bit low. Your volume.
Okay. Is it better now?
Yeah,
Should
yeah,
I
definitely.
take
Thank
it
you.
closer to me? Yeah. Okay. Thank you. So sorry about that. So yeah, when you're developing a game production, the art of your business, what you do best is to build the best possible experience for your players. So you focus on the game design, on assets production, on the technology to enable fun for your gamers. But then, if you're thinking about adding social features such as friend lists, leaderboards, challenges, or eventually even multiplayer gameplay, those features they require infrastructure, which means server management, data storage, live operation, scaling in order to accommodate the growth of your audience, and those are domains of expertise that are usually outside of game development. So let's take the example of a backend service. The first thing you might be looking at is a three-tier web application, a web server for the presentation layer, what we have that we have here, application servers for the business logic, and database server for persistency of the data. But that's when you are going to start to ask yourself some questions. First, how do you keep those servers responding quickly to your players, maintaining low latency? David already talked about that. Quick response, especially when you have players all around the world. You also want to ensure that it's reliable, it remains available. Server can crash, network links can get broken. Our CTO, Werner Vogels, often quote, everything fails all the time. You need to be prepared for that. You need to be prepared for failure to make sure that you can respond to them and make your service reliable. And then you're also storing data from your players. They need to trust you that it won't be compromised. So how do you secure those accesses or prevent attacks? Servers also require management, patching, upgrades. Uh, who's going to be responsible for that? You might also need to update your service. So how do you deploy new features? How do you deploy it easily? And finally, you want to make sure you control the costs of your infrastructure, and especially the cost per player. So those are what we call pillars of the AWS well-architected infrastructures, and that's what you should aim at to ensure the best possible players experience. And it's not easy. You'll be looking at new technologies, how to set up network and infrastructure, operate the service when the game goes live. This has also to be done usually under tight constraint. Time to market is important in games. Resources are scarce and costly. It's not easy to find developers. And success is unpredictable. I mean, you don't want to pay for many servers if you don't get enough players to fill them, but you also wish to be successful and be able to answer to all the players that are going to know, but you don't know how much player you can expect when you release your game. So here comes serverless into the picture, and here is how it can help. Serverless is regarded as the native architecture for the cloud. There is no or limited provisioning and management requires. So you don't need to worry about configuring servers or patching them anymore. Those serverless services, they usually take care of scaling for you. So it will help you deal with the unpredictability of your workload. They follow a pay-per-usage approach, so it enables you to easily control your cost per player as your platform, your infrastructure will grow and shrink with the number of players that you have. Finally, those services, they usually implement best practices for security and availability. So they are providing those best practices to your services with limited efforts. Redundancy is usually built in, as well as security. So you only need to focus on those points within your code, within your own business logic. So those are reasons why you should consider serverless to develop backend services for your game. Serverless, when we develop serverless services at AWS, it's made for builders. For example, you can code a Lambda function with the language of your choice, JavaScript, Python, Node.js, C Sharp, Go, and even more. You don't need to learn new languages. They scale with your audience, so you do not have to fear investing in useless servers or not having enough to cope with success. Easy development and pay-as-you-go model are lowering the risk when it comes to iterate and test new features. It's easy and cheap to set up temporary environments for developers. So all of these are the keys to unlock quick cycles of innovation for your players. So that's why a lot of customers now are implementing a serverless first strategy when it comes to develop new services. And serverless first does not mean that you will always use serverless services, but those are the first services you will look at when it comes to development. So let's look at our 3-tier application with a serverless version. The layers are actually quite similar, but there are some key differences. Specifically, what we are looking at here is what we call a microservice. It's usually what you will do is decompose your application into different small services that all have a very specific business function. And many of our customers, they run dozens, hundreds, or even thousands of these kinds of services to improve the scalability and resilience, because that means that one service failure will not impact as much thing as it would with a big single service. And you can scale those services independently from each other. This is basically a big topic, microservices, and that's not the one that I'm going to discuss in details today. Then another most difference is in the integration and communication. We're usually using a combination of events and queues to have asynchronous interaction between the different elements of the service, and an API to communicate with external services or other services. It also enables you to have a purpose-built data strategy. It means one database for one usage. At AWS, we provide you with different kind of databases that you can use. There are SQL databases like Aurora, NoSQL databases like DynamoDB or DocumentDB for document-based databases. Those are the fact that you are developing microservices will enable you to use the best database for the usage, and you're not locked with one database technology. Serverless also enables you or implies that you're going to build a DevOps culture. DevOps means you build it, you run it, You will have teams of developers that are made of builders and operators. Operators do not need to have a deep knowledge of the hardware running behind the scene. They are skilled in developing tools to automate and monitor things carefully and efficiently. Oops, sorry, I pushed the wrong button. So they do that through developing CI/CD pipelines, for example, as well as maintaining the way logs, backups, and are gathered and exploited. Builders, they will have full access to a playground where they can actually test their new and innovative features. Once it's ready for deployment, they will push the code and in the CI/CD pipeline, and this CI/CD pipeline will automate deployment into the staging and production environment, including, of course, build and test phases. Developers will also have read access to the logs and backups and insight tools to be able to investigate any issues happening within the staging or production or environment. So you have a small team, but that's able to build and run a services on its own. So here are some of AWS services that you can use to build serverless applications. Those are the most common building blocks. Here on the top left, you have AWS Lambda. We've been talking about it before. It's function as a service. So it executes code in isolated functions. You have also the options to use AWS Fargate. It's a serverless hosting service for containerized application. So it can be used in coordination with orchestration services such as ECS, Elastic Container Service, or EKS, Elastic Kubernetes Service. Then you have various ways of triggering those code execution. Amazon API Gateway is a good service to build a REST API, or AWS AppSync that can help you build GraphQL endpoints. You can also trigger the code asynchronously through messaging and queues, as we've seen in the high-level architecture before. So SNS is single notification service, and SQS is a simple queue service. And you can also orchestrate longer execution flows using AWS step function and create event-driven architectures using Amazon Event Bridge. And in terms of databases, as I mentioned before, you are free to use serverless technologies such as Amazon DynamoDB, which is a key value store, so NoSQL database, and Aurora serverless. There is a V2 version that's going to be released soon that is currently in preview. That's going to be very efficient to do SQL in a serverless way. Let's look also at an example of a CI/CD pipeline, as it's been discussed previously. In this example, you will have events such as a push of code that will come in AWS code commit. This is a Git repository service for hosting Git repository. And then you have AWS code pipeline that's going to orchestrate your whole deployment. Code build will help you build your code and also perform unit testing, for example. Then using AWS CloudFormation, which is infrastructure as code, so it describes your infrastructure inside templates. You will be able to deploy this in a staging environment, run integration tests on your staging environment. And if those tests are successful, then you can use the same CloudFormation that you had previously to deploy into production. So what can serverless be used for? It can be used for a lot of different things, from web applications, backends for apps and services, mobile backends, data processing. There's a lot of usage for Lambda to do data processing in real time. It can power chatbots and things like Alexa skills. And it can also be used to do IT automation, for example, to be triggered when there are some events happening on your infrastructure. You can react to events such as a scaling of servers or anomaly in your metrics, and run a Lambda function that's going to change your infrastructure to cope with this, with the issues. Let's give you a few examples of this. Square Enix, they had an application for Dragon Quest X, a companion app and a website where you could like upload a picture, but the picture required processing. They had to do watermarking and also resizing, for example, before they could display them on a website. They were doing that on their own servers, and it was very resource intensive. Servers usually have to process 200 to 300 pictures a minute, but when they had some events, some Christmas period or New Year's Eve event, it could go up to 6,000 images per minute. And their infrastructure in time of peak, the processing could take several hours to complete. So it took several hours when the user uploaded the picture before they could see the picture on the website, which was not really good from the player's point of view. So they decided to move to a serverless approach. Picture would be sent to an Amazon S3 bucket, and it was a Lambda function that would perform the processing on the picture and send the result to an SQS queue that will be processed by their website to display the images when they were ready to be displayed. And as a result, during one of their event on a New Year's Eve, the rate of uploading photos went up to more than 6,000 screenshots per minute, and they were able to keep the processing time under 10 seconds for the players. Another example of developing serverless in a gaming context. Quantic Dream, they were thinking, it's a game developer in Paris. They're famous for hits such as Detroit Become Human. Um, the studio, the development studio, they already consider using cloud workstation. You've seen it maybe with the AMD session before. Cloud workstation to be able to recruit and work with talents from all over the world. And when the COVID-19 pandemic forced them to close their office, the project was accelerated as their own team could not work anymore. So in order to, but the thing is, they were able to create workstation in the cloud, but they needed a way to facilitate and secure their team's access and connection to those workstations. So they decided to develop an API backend using API Gateway and AWS Lambda. When a client connects to the backend, a Lambda function finds the right workstation for the user, starts it if it has been stopped, and gives the IP address to the client so that it can automatically connect the user to the workstation. So they were able to deploy an API to give secure access to those workstations in less than 2 weeks. So let's look at the example now in a little bit more detail of what it looks like to create a presence API using those serverless technologies. So let's imagine you have a game project that has some API based on AWS AppSync to provide the features such as friends list or leaderboard. So AppSync is a fully managed service that makes it easy to develop and deploy GraphQL API. So there's a GraphQL proxy here. And it's handling the heavy lifting of securely connecting your data sources, which are called resolvers, to services like Lambda, DynamoDB, or things like that. And you describe your schema with GraphQL, and AppSync calls those resolvers for you and answer to your operation. It's also interesting because it can it can be used for real-time updates. There's a PubSub engine built in the GraphQL, the AppSync infrastructure. So clients can subscribe to certain operations, and when the change is happening on the backend, the clients can be notified of those change. And clients use the WebSocket connection to do so. So what we want to add here is a way for the clients, the different players, or even the other services to be notified when players are connecting or disconnecting from the backend. So let's see how we can do that with AWS service. Let's take a look at the schema first, defining the data. So first we have a status that can be online or offline for the different player. And then we define a type so this is the GraphQL definition of our schema. We define a type which is composed of an ID, so that identify the player and its status. So this change type is the type that will be returned by our API each time we perform some operation on it. For example, we can perform some specific, there's a specific type in GraphQL that's called query. So it means that we are querying data from the backend. So we have two queries here. We have a status query that queries the status of a specific player ID, and an heartbeat query that will be used to inform our backend that we are still connected to it. So this is something that will be sent to the backend at regular time intervals. We also have a mutation type, which means that it's a query that will modify something on the backend. So there is a connect and disconnect mutation that will inform the backend that the player is connected or disconnected. And finally, there's a type called subscription. So this informed the backend, our GraphQL deployment, AppSync deployment, sorry, that when there is a call to those mutations, then we subscribe to them, and the notification will be sent on the WebSocket for this subscription. So this is something that's specific to AppSync. You need to use the annotation AWS subscribe to do that. For data storage, we choose to use Redis on the Amazon Elasticache deployment. We use sorted sets because what we want to have is an easy way to find out when we send an heartbeat, we store the timestamp of the heartbeat, and we want to quickly retrieve timestamps that are older than the timeout for disconnection. So yeah, so that's the schema. Here is the infrastructure. So as usual, inside AWS, usually infrastructure are deployed inside what we call the VPC, a virtual private cloud. So this is your own isolated environment in the cloud. And inside the VPC, you can define subnets, which have their own properties. So we have a first subnet that's called isolated. That means that it's completely private. Nobody can access it from outside the VPC. That's used to deploy our Elasticache cluster for Redis. Then we have another subnet that is a private, where we deploy our Lambda function resolvers for AppSync. And we have a specific timeout function here that is going to poll our cache to see if there are connections, timestamps that are older than the timeout. And this Lambda functions requires to send a mutation to AppSync in order to notify the other players that one player has been disconnected. So for that, we have to deploy a NAT gateway inside our VPC. A NAT gateway just gives an access to our Lambda function to AppSync, because AppSync, as it's a managed service, it's deployed outside of your VPC. So you need an internet access to access it in that case. So this is a demo I recorded of a way to deploy it. Here I'm gonna deploy a Cloud9 environment on AWS. Why I'm doing so? Because it's very easy to deploy, as you can see here, and it comes with everything pre-installed to use AWS tools such as the CLI or the CDK that we are going to use. And it's a fully online environment, so it's available in your browser. And this environment, you will see it after. You can use it to deploy and code for your infrastructure. And if you don't use it for a certain amount of time, it gets stopped. So you are not paying for the server if you don't use it. To deploy the infrastructure, we're using the CDK, so it's a cloud development kit. CDK is a set of tools that helps you build your infrastructure as code. What it gives you at the end is CloudFormation templates, for those who know about CloudFormation, and those templates can be deployed inside AWS to deploy your infrastructure. The advantage of the CDK, as far as I'm concerned, is that it uses code directly, so it's a little bit more flexible and dynamic. As you see, it's I'm using TypeScript here, but it's also available in other languages such as Python, for example, or I think Java. Java is also available, or Go. And it also, the interesting part is that it gives you a construct to simplify your development. So here, for example, I'm using the VPC construct. And to build the VPC construct, you use you define some properties of your VPC, like the subnet configuration. I'm defining a configuration with three subnet here: isolated, private, and public. So that's the one you've seen in the infrastructure before. And what's interesting here that, as I mentioned, that I want a private a subnet for my Lambda function, the construct knows that it has to add a NAT gateway to give internet access for those Lambda functions. So you don't have to mention it here. It's already built in inside the construct, and we are going to see that in the video. So here is my Cloud9 environment that has been already set up. So I'm creating a directory. So you see it's a classic IDE. I'm initializing a CDK project with the TypeScript language. So as a lot of frameworks, it's going to create different files, a Git repository for me to that I can use in a CI/CD environment. It's going to install different modules as well. And once sorry, I think it's it's the same video here. Let me go to the next one. Once it's deployed, you can start writing your code. So it's a small demo stack. I'm going to import the module EC2 that's going to help me define my VPC. And it's very modular. You see there's a module for each service inside AWS. So I'm creating the VPC, and what is also cool is that all the modules are very documented. So you can see here when I'm creating a VPC, I can have access to a lot of different information about what is required to construct this VPC. So the different parameters that needs to be set up, and when I start to set up the properties here, you will see that all the properties are listed here, and you have a description of what are the properties, if they are required or not, and all those things. So I'm going to copy and paste the code that I've showed you before here, and then I'm going to run. So you can see the code here. There's no mention of any NAT gateway of any kind. And then I'm going to run a command called cdk-synth, which is a synthesize. So it's going to create our YAML template for CloudFormation on the background directly. And now you can see the CloudFormation template. It's much more complicated than the code itself, and it created a lot of different things like root table and subnet root table association, because it knows that when you create a construct like that, you want something that an infrastructure that's usually used in those cases. So. And our NAT gateway is here too. And you don't have to worry too much about those resources. They're created for you, and they are created according to the best practices and recommendation from AWS. And when you then another function is deploy with the CDK. So this will deploy your template, and as you see, you get a lot of information about what you're going to deploy, the different policy changes, the security group changes. So, and it's gonna ask you if you're really sure about what you want to deploy. And once it's deployed, you get some output information. So, for example, here I get an output of my Presence API endpoint, the API key that I need to use to connect to it. And those information, you can use it directly inside your CI/CD pipelines to do something like unit test or integration test. And in fact, in the GitHub repository for the example, you have some example of that. Let's quickly look at the Lambda function that we use as a resolver for our API. Lambda function, they are basically usually divided in two parts. First, there's an initialization part connection. David mentioned that in this presentation. When you use Lambda function, you have something like a cold start, which means that the first request that you will do, the Lambda service needs to set up a container and to run the Lambda function inside it. But once this initialization is done, the Lambda function can be reused for further calls. So when you have a lot of concurrent calls, you won't really notice the cold start because it will happen only once. So it's usually a good practice to put initialization connections inside this part of the function outside of the handler. The handler is what is actually called by the event. So when AppSync is receiving something, it will send an event to our function, and that's where we're going to use it. So this is the heartbeat handler. So what it's going to do is mainly retrieving the ID from the event that we've said, and using a function called deadadd from Redis to add the information of the timestamp and ID of the player. Sorry. So here I deployed the different function in my stack, and the first I'm going to show you the status function here. So it's basically kind of the same. It's only retrieving the score to return according to the score. It will return online offline for the player. And what you can do inside the console is configure a test event here. So you can get a test event, put an ID inside it, give it a name, and save it. So I give it a name, and then I create the test event. And once the test event is created, you can test your function directly from the console, and you have information about what happens. And as you can see, our status give us an offline status. If I go to the heartbeat function now, so I'm going to check if everything's working as I expect. I'm going to use my test event again because it's the same parameter from the function. And when I test the function, as you can see, I get an online result on the status. So it has updated the Redis database. And when I call the status function again, this time I get an online result. So that's a way you can check if your functions are working properly. Let's see how we handle disconnections inside our deployment. We handle disconnection with the timeout function, as I've mentioned before. So it's a scheduled event. You can use Event Bridge to trigger Lambda function at regular interval. This event will just get data from our Redis cluster, and then it will call a new mutation, a disconnected mutation. And this mutation will then notify all the players that have subscribed to it directly. We can do that by adding the mutation inside our schema here, and also add it in our disconnected event. One small change you can see here, there's another annotation for the disconnected mutation, which is at AWS IAM. This means that as our mutation will only be called by internal AWS services, such as Lambda, you can inform AppSync that you give the Lambda function permissions to call AppSync, so it doesn't have to use API key or things like that. It can call the service directly. Now, the thing with the previous infrastructure is that disconnected events uh, are isolated. They require an additional mutation, which might be not good because you need the client has to subscribe to different mutation. And the thing is, if you want also to inform other services that the client has been disconnected, you don't have you don't have any way to get this information. This is why we want to evolve our infrastructure to an event-based infrastructure. So we are using Amazon Event Bridge here. It's a serverless event bus that makes it easy to connect applications together. Event Bridge delivers a stream of real-time data from event sources and routes them to targets like AWS Lambda. So here, what we're going to do is that every time our disconnect mutation is called, or the timeout function sees a disconnection, we're going to send an event to Event Bridge. And this event will be the same for both events. So any type of disconnection will be registered into Event Bridge, and will be able to inform other services, targets, that the event happened. The other interesting thing about Event Bridge is that it allows to define what we call private endpoints. Those are endpoints that you can have inside your VPC. So those Lambda function will be able to directly connect to the endpoint, and they don't require any NAT gateway anymore. So this makes our application even more secure. And then we will also add a new Lambda function, which is called onDisconnect, that will be a target of this disconnection event, and that will be able to call AppSync. And this Lambda function will not be inside the VPC, so that it can be that it can directly call AppSync here. Yeah, sorry. So what we do inside our CDK script, here is a way to define a rule for AWS Event Bridge. So we use an event bus, and what we do is we define a pattern. So every time an event that has this kind of detail and is coming from our Presence API, we will target one of our Lambda function. And in the CDK, it's very easy to define targets from resources that are already existing. We just use one function that we already define and add it as an event target. And that will register the notification. This is the Lambda function, the handler of the Lambda function that is the timeout Lambda function. So as you see here, we modify it so that it can use Event Bridge. So what it's going to do, it's first using some transaction on Redis with these two functions to retrieve the timestamp of player IDs that have not sent heartbeat from some time. Once it got those IDs here, if there are any IDs, then it will divide those IDs in list of 10, because you cannot send more than 10 events to an event bus at a time, and it will push those events to Event Bridge using a put events function, and then get the results to know if everything went well. So we can have a quick look at our AppSync API. So this is the console for AppSync. As you see, we have our schema here. We have our resolvers on the right, and you can inside the console directly input queries. So I'm gonna do a heartbeat for test here, and it's shows the status as being online because I'm doing an heartbeat. Then I'm gonna check that the status is indeed online. And what I can do is open two different, test one is offline, of course. I can open two different tabs on my browser to check that the subscription is working well. So that's one I'm gonna do in the, in the next video here. So test one is offline, and I can also call mutation. So for example, connect for test, for the test ID. And in a different tab, I can do a subscription. So I'm going to register a subscription to get the status of the test player. So as you can see, it's subscribed to Station. In the previous tab, I'm going to do a connect. And as you can see, I received an online notification here on the right. And if I do a disconnect now from the mutation, and I go back to the subscription type, I now have an offline result. And if I leave the subscription running for some time, you will see the same result. So yeah, just to do a quick wrap up, because I see that I've been maybe a little bit longer than expected. Sorry about that. Serverless first strategy is recommended for a new application developed on AWS. It's especially if you want to quickly develop a backend on the game. It minimizes your resource needs, simplify operation, and enable fast iteration. There are some documentation here about the CDK. There is a link also to the GitHub for the sample of the AppSync Presence API, and a blog post that explaining that into details. The source code comes with a little application that you can use to test the API. So maybe I'll be sharing it in the YouTube channel after that. Yeah, that's it. That's it for me. Thank you for listening. Hope that was interesting for everybody.